So we will begin with our next chapter under MEC 551 Thermal Engineering. So here we will be focusing on air conditioning, which will be as an extension of our refrigeration cycles. So as you know, we as human being have an inherent weakness. We want to be very comfortable. We want to live in an environment that is neither hot nor cold, neither humid nor dry, right? But this comfort does not come easily, since the desires of the human body and weather usually are not quite compatible. So you can have a very hot weather or a very cold weather. Achieving comfort requires a constant struggle against the factors that cause discomfort, such as high or low temperatures and high or low humidity. So as an engineer, so it is our duty to help people to feel comfortable. So finally, it did not take long for people to realize that they could not change the weather in an area or the external conditions, but we can always change the condition in an confined space, such as a house or a workplace, right? So traditionally, this was done by placing fire and simple indoor heating system. Today we have modern air conditioning system that can heat, cool, humidify, dehumidify, clean, and even deodorize the air. In other words, condition the air to people's desire. Right? Air conditioning is nothing but a system designed to satisfy the needs of human body. Therefore, it is essential that we understand the thermodynamics aspects of this system. So that will be the chapter that we'll be discussing in depth on how to do heating, how to do cooling, how to do humidifying, how to do dehumidifying, or any combination of these processes. So the objectives of this chapter are as follow. So for point number one, we will be exploring the properties of air mixtures, learn what are the properties of air mixtures in terms of temperature and humidity control. Then you will be also taught on how to use psychometric chart to solve problems related to air conditioning. And objective number three is related to basic processes of air conditioning. We have heating. We are very familiar with cooling in Malaysia because this is what we get. But if you are living in a winter climate countries like UK, during winter, you will need to heat up the room instead of cooling the room. Now we also have humidification, where you add moisture to the air. We also have dehumidification, where you absorb the moisture out of the air. And adiabatic mixing is about introducing fresh air into the system. Then we also have objective number 4 on cooling tower. We will learn a bit on its operation and its application in air conditioning. So let's begin with our introduction. So what is air conditioning? So air conditioning is nothing but it's a process of treating air to control simultaneously. So here we have the word simultaneously. So what you're doing is you are treating air around you, right? So air conditioning is nothing but a process of treating air. Why do you treat the air? Because you want to control simultaneously. The first thing, it's its temperature. So if you feel hot at home, you will switch on your air conditioner because you want to bring down the temperature in the confined space where you are staying in. So that is controlling the temperature. So the next thing that you want to control is the humidity. So we will cover in this part of this chapter what is the definition of humidity, and you will see that in Malaysia our humidity is quite high. It can be as high as 80 to 90%. So we need to control that so that you can achieve the human comfort level that you want from the air conditioning processes. So those are the two controls that you want to have when you want to switch on your air conditioner. The next is cleanliness. So air around us might be dirty, so you need to filter out the air. So there's a lot of dust in the air. So the air conditioning, one of the objective of having an air conditioning is to also clean the air around us, so that you can maintain the cleanliness in a confined space where air conditioning is running. And thirdly is the distribution. So if you have a central air conditioning system, you will need to distribute this cool or hot air around the entire distribution system, and this air conditioning system allows you to do that. So as you can see here, so we have a process. So air conditioning is nothing but a process of treating air to control simultaneously these four parameters. The temperature, now the temperature here is either you can reduce the temperature or you can increase the temperature. So in Malaysia, definitely, because our mean temperature is around 35 degrees Celsius, so we will then use the air conditioning to lower down the temperature to almost 24 degrees Celsius. So that's the human comfort temperature. Humidity in Malaysia is high too, so we can use the air conditioning system to reduce the humidity to the comfort that we are comfortable with. And there are a lot of dust that we have in the air around us, so you can use the air conditioning system to clean the air, so that you can trap the dust in the air conditioning system, and the air that is delivered to you after the air conditioning process is clean. And you also need to distribute air. As you can see in the classrooms, we have a lot of air conditioning ducts that distributes cool and treated air to all the rooms. So this is some introduction. So air conditioning, as we have discussed, is purpose to maintain a confined space at the desired conditions. And how do you do that? Is by either heating, or you can cool down the air, or you can humidify if the humidity level is too low, or you can dehumidify if the humidity is too high. So these are the four processes that you can have in order to maintain a confined space at the desired conditions. Now what I So human body comfort depends on these three factors. So the factors are temperature, humidity, and air motion. So we want to live in an environment that is neither hot nor cold, neither humid or dry. However, comfort does not come easily, since the desire of the human body and the weather usually are not compatible. Right? So just like in Malaysia, the temperature of the surrounding can be in this range, 27 to 42 degrees Celsius according to monsoon season. And the comfortable temperature that suits our human body comfort is between the range of 20 to 24. So achieving comfort requires a constant struggle against the factors that cause discomfort, such as high or low temperatures and high or low humidity. So if you look at our human body can be viewed as a heat engine whose energy input is food. As with any other heat engine, the human body generates waste heat that must be rejected to the environment if the body is to continue operating. Now, if you look at the rate of heat generation, it depends on the level of activity that we are in. So if you are an average adult male and if you are sleeping, you will be generating about 87 watts of energy. And this is heat energy that is released into the surrounding. If you are resting or doing your homework, you will be releasing about 115 watts. And if you are doing heavy physical work, then you will be releasing almost 500 watts of energy. So our deep body temperature, if you are a healthy person, is always held constant to about 37 degrees Celsius. Now, your body will feel comfortable if you are in an environment in which you can dissipate this waste heat comfortably. Now, we know heat transfer is proportional to the temperature difference. Therefore, if you are in a cold environment, for an example, if you go to Cameron Highlands, our body loses more heat than it normally generates, which results in feeling of discomfort. Now the body will try to minimize this energy loss by cutting down the blood circulation near the skin, and this will cause a lot of discomfort to you. So in order to avoid that, what we will do is we will add on more clothes so that we will become much more comfortable, and this will introduce a thick layer between our body and the environment, and this becomes an insulation layer so that you can remain comfortable in a cold climate. Now if you have a hot environment like what we have in Malaysia, we are in a situation where we do not seem to be dissipating enough heat from our bodies, and we feel as if we are going to burst. So what we do is we dress very lightly so that it is easier for heat to get away from our bodies, and we reduce the level of activity to minimize the rate of waste heat generation in the body. Now the simplest way to do that is we can also turn on the fan to continuously replace the warmer air layer that forms around our bodies as a result of body heat by the cooler air in other parts of the room. Right? So this is, we also sweat. So in a hot environment, as you can experience in Malaysia, we also perspire, and then by sweating more, as this sweat evaporates, it absorbs our heat. So this heat is in the form of latent heat from the body, and once this sweat evaporates, it cools our body down. Now if you sweat a lot, and prolonged sweating without any fluid intake will cause dehydration, right? And this will also reduce sweating, which may lead to a rise in body temperature and cause you a heat stroke. So as you can see from the slide here, the comfort of the human body depends primarily on these three factors. So the temperature that we are comfortable in should be maintained between 20 to 24 degrees Celsius. And you can use air conditioning easily to maintain this. In a hot climate country like Malaysia, we use air conditioning to absorb the heat out of the confined space and reject it outside into the surrounding. But let's say if you are in a cold climate country during winter, obviously the temperature outside is going to be lower than this temperature range. Then what you do is, instead of absorbing heat from the confined space, then you will be adding heat into the confined space so that you can raise the temperature of the room to this comfortable temperature range. Another factor that affects your human body comfort is the humidity. So humidity must be maintained between 40 to 60%. So humidity is nothing but the amount of moisture present in air. So the higher the moisture, the higher the humidity. So Malaysia, our humidity is between 70 to 85%. So we can actually use air conditioning to reduce the humidity so that we can achieve the comfortable level, which is between 40 to 60%. Now air motion also plays an important role in human comfort. It removes the warm, moist air that builds up around the body and replaces it with fresh air. So therefore, air motion improves heat rejection by both convection and evaporation. Now air motion should be strong enough to remove heat and moisture from the vicinity of the body, but gentle enough to be unnoticed. So you don't want a high velocity air blowing over your body, because that becomes uncomfortable. So your air ventilation and the velocity of air motion is very important. So these are the three factors that are important in order to achieve the human body comfort. Now there are other factors that affects this comfort. The first is the air cleanliness. Now if you remember, we need to clean our air from the dust, and 80 to 90% of the dust constitutes of human body dead skin. So we need to clean this air so the air can be filtered through the air conditioning, and then the air that is then delivered to you will be cleaner than the air that was in the confined space. And we also need to make sure that the air that is being conditioned through the air conditioning process is free from any odor or any smell. In certain cases, you can also control the radiation and other factors that we will discuss later in the presentation. So these are the human body comfort, and then it depends on these three factors. And remember, in the subsequent presentation, we will be learning on how to control these two parameters, especially the temperature and humidity, so that you can achieve the human body comfort between 20 to 24 degrees Celsius and the humidity level between 40 to 60. Now, if you look at this diagram, it shows that we use conditioned air in our daily life. If you have a medium-sized hospital, the energy usage is shown here in a pie chart, and you will see that the air conditioning constitutes almost about 40% of the energy used. In a large hotel, air conditioning can constitute almost about 54% of the total energy used for that premise. In a large office building, we will see that 50% of the energy bill comes from air conditioning alone. So like it or not, air conditioning plays a very important role in our daily life. Whether you go to a hospital, whether you are in a hotel, whether you are in an office building, and even if you are in an institution like UITM, you need air conditioning badly. So we depend a lot on air conditioning to achieve our human comfort. So next, pay attention that we badly need conditioned air for other purposes too, not just for us to reach the human comfort level. We also need air conditioning to maintain a uniform temperature during manufacturing processes. This is because any fluctuating air temperature will result in poor product quality. So if you have non-uniform temperature during manufacturing processes, it can cause shrinkage, and this will result in poor product quality. And you also need dry air in textile industry and library. Now consider library. In a library, we have a lot of books. And if you have moist air in the library, this will result in fungus formation in textile or books. So in order to avoid this, we can treat the air in the textile industry and also the library so that we can only deliver dry air without any moisture, so that you don't have this issue of fungus formation. Next, we also need conditioned air in hospital or operation theater or in a clean room. So clean room is where you manufacture your integrated circuits, the wafers, all right? So you need uh, very clean air in a clean room where you manufacture wafers. It has to be dust free. Even a single speck of dust which falls onto a wafer can destroy the entire wafer. So in our hospital, we need to make sure that the bacteria and dust are filtered and removed from the air. Because if you have a lot of bacteria floating around in the hospital, this can cause infection and patients might die because of septic shock caused by the bacteria. And finally, we also need cool air in computer and server rooms. So server rooms tend to become hot because they process data in a very big scale, and this releases a lot of heat. So in order to maintain the temperature in the computer and server room, we need to supply cool air. So this will help in cooling of electronic equipment, and if you do that, this becomes very essential to avoid damage, because any computer or server room exposed to high temperatures will result in electronic equipment damage. So cool air supplied to these rooms will help to avoid this. So you can see now, air conditioning is more than cool air for human comfort. We need air conditioning for many applications. Now there are various applications of air conditioning, and then if you have time you can actually go and have a look at this ASHRAE handbook for standard design requirement. So ASHRAE is acronym for American Society of Heating, Refrigerating and Air Conditioning Engineers. This ASHRAE book handbook is available online, so I've provided you with a link, so you can actually go and have a look at this handbook, and then see what are the type of air conditionings they have, what are the standards that they follow. If you intend to become a HVAC engineer once you graduate, then this is one of the most important book that you must have with you, because all your design requirements, design conditions are specified clearly in this handbook. So in this slide we will see how an air conditioner works. So as you can see in the diagram here, you have the basic components that we have covered in our refrigeration cycle. So what you see here, you have a compressor, you have a condenser, you have an expansion valve, you have an evaporator. So basically air conditioners, they work with the principle of refrigeration cycle. So what happened is the air from the confined space is actually pulled into the duct, all right, with the help of a fan here which is located near to the evaporator. So this air needs to be conditioned. So if you are in a confined space where you need to cool down the air temperature, so this air is then channeled through the evaporator. So as the air flows through the evaporator, the heat is absorbed by the refrigerant in the evaporator. So as a result of that, the cooled air is then delivered to the confined space. So this is how you cool down the air. Now the heat absorbed by the evaporator is then sent to the condenser of the air conditioner. So with the help of another fan here, this heat is then expelled to the surrounding atmosphere. So as a result of that, the refrigerant is now cooled and then can be recycled back into the refrigeration cycle to continue absorbing heat from the confined space as explained earlier. So as you see, the refrigeration cycle is the basis of how air conditioner works. All right, so we have compressors, condenser, expansion valve, and evaporator. And this is where you get the cooled air coming in, and the condenser is the place where you reject the heat from the refrigeration cycle. Now we go to the psychrometry. Now what is the psychrometry? Psychrometry is the study of air. So what are the constituents of air? All right, so if you look at this statement, psychrometry is the science of studying the thermodynamic properties of moist air and the use of these properties to analyze conditions and processes involving moist air, that is the study of atmospheric air. Now if you look at these two words, you have moist air, so meaning to say that you have air embedded with some moisture, right? So that is the psychrometry. Now air is a mixture of nitrogen with oxygen and some small amount of some other gases. So what are these gases? We will see in a while. So air in the atmosphere normally contains some water vapor, so we call it as moisture and refer to as the atmospheric air. So the water vapor in the air in terms of content by mass can be between 0 to 3%. So if you have 0% mass of water vapor, then the air in the atmosphere is called as dry air. All right. So if you have some moisture in it, then it becomes what you call the mixture of air and moisture. So air that contains no vapor, so no vapor means 0% water vapor, we call it as dry air. So these are the constituents of atmospheric air. So you can see here we have nitrogen, oxygen, argon, carbon dioxide and hydrogen.
Nitrogen constitutes almost about 78% by volume. Oxygen is about 21% by volume. And then the balance less about 1% constitutes of argon, carbon dioxide and hydrogen. And this is again, all these parameters are represented in a pie chart here. You can see that the major constituent of atmospheric air is nothing but your nitrogen. Then you have about 21% of oxygen, and then about less than 1% it consists of argon, xenon, neon, hydrogen, helium, krypton and carbon dioxide. Now for dry and water vapor of atmospheric air, the atmospheric air consists of dry air and water vapor. So this atmospheric air, you have two constituents. One is the dry air, the other one is the water vapor. Now we will now go to Dalton's law. So in Dalton's law, let's look at it. Partial pressure states that the total pressure of the gases is the sum of the partial pressures. So the partial pressures in atmospheric air constitutes of the pressure of dry air and the pressure of water vapor, right? So that is based on Dalton's law. So the total pressure constitutes of pressure of dry air plus pressure of water vapor. So that is the total pressure. For an example, if you have atmospheric pressure of 1 atm, so that 1 atm constitutes of pressure of air plus pressure of water vapor. So the other point that to be considered here is your volume, or the enthalpy of the mixture of gases is the same as the volume occupied, or the enthalpy of the constituents of each gas at its partial pressure, right? So we will see in examples on how to use this formula. So bear in mind, based on Dalton's law, the total pressure of atmospheric air constitutes of the partial pressure of air, dry air, plus partial pressure of water vapor. Now the temperature of atmospheric air in air conditioning applications ranges from negative 10 degrees Celsius to about 50 degrees Celsius. So whenever you have this range, any temperature that is below 50 degrees Celsius for atmospheric air, then you can treat the air to be an ideal gas. So the moment you can treat the air as an ideal gas, you can start using the formula PV equals to nRT. And as a result of that, then you can find the enthalpy based on this formula. Cp, specific heat capacity of air, and then this is the temperature. Now bear in mind, this temperature is always in degrees Celsius. And the specific heat capacity for air, the unit is always in kilojoule per kilogram degree C. So we will see in our examples later on how to use this formula. So this is the enthalpy of air. Alright, so bear in mind the temperature is always taken in degrees Celsius, not in Kelvin. Alright, so this is another note on dry and water vapor of atmospheric air. So as you can see here, partial pressure of water vapor is usually referred to as the vapor pressure, and it is the pressure water vapor would exert if it existed alone at the temperature and volume of atmospheric air. So since water vapor is an ideal gas, so the enthalpy of water vapor is a function of temperature only, so which we have seen earlier, right? So this can also be observed from the TS diagram. So we are given a TS diagram here, right? So where you can see the constant enthalpy lines. So this constant enthalpy lines coincide with constant temperature lines at temperature below 50 degrees Celsius. So at any temperature below 50 degrees Celsius, your H is considered to be constant. So therefore, the enthalpy of water vapor in air can be taken to be equal to the enthalpy of saturated vapor at the same temperature, right? So this will lead to, for these conditions, so the enthalpy of water vapor can be approximated based on this formula. So since, as what we've discussed, so saturation pressure of water vapor in air mixture is below this, or we can say that the temperature is always below 50 degrees Celsius, And if you use this formula, right, as you can see from this table, so if you find the enthalpy based on the equation given here, and you find the enthalpy based on the table given in the property table and charts, you will see that the difference is very small for temperature range between -10 to 50 degrees Celsius. So for this range, you can safely use this equation to find out the enthalpy. Again, point to note, this temperature here is always in degrees C, not in Kelvin. So we'll be using this formula again and again in calculating our enthalpies in our subsequent sections. Now let's look at what is specific and relative humidity of air. So these formulas are important. So humidity is nothing but amount of water vapor in the air. Higher humidity reduces the effectiveness of sweating. So if the humidity is high, our sweat will not be able to evaporate. So this will reduce our effectiveness of sweating, and this will in turn slow down the cooling of the body by reducing the rate of evaporation of moisture from the skin. So as mentioned earlier in our presentation, the humidity level in Malaysia is very, very high. So you become very lethargic when you start sweating because it takes a very long time for the sweats to evaporate when the humidity is very, very high. So the main measurement of humidity is given as follow. So the first parameter that we can use to measure humidity is called specific humidity, or we can also call it as absolute humidity. The symbol is given here. The symbol is called omega. So this is defined as the ratio of the amount of moisture in the air to the amount of dry air. So this is given in the formula here. All right. So omega is the amount of moisture in the air to the amount of dry air. So this is based on the definition, and then you can modify this equation to introduce your partial pressure of your water vapor. 0.622 times partial pressure of water vapor divided by this P here is the total pressure minus the partial pressure of water vapor again. So as you can see here, there are no units for omega, but we quantify it in terms of kilogram of moisture to kilogram of dry air. So specific humidity, if you want to specify it, it is always in terms of kilogram of water moisture to kilogram of dry air. So this is the unit, kilogram of H2O divided by kilogram of. Okay, now we'll go on to the relative humidity. Relative humidity is denoted by this symbol phi. So relative humidity represents the amount of moisture the air holds to the maximum amount of moisture the air can hold at the same temperature. Now the amount of moisture in the air has a definite effect on how comfortable we feel in an environment. However, the comfort level depends more on the amount of moisture the air holds relative to the maximum amount of moisture the air can hold at the same temperature. Now the ratio between these two quantities, is called relative humidity. So mass of water vapor in air divided by mass of saturated moisture in air. So that is given in based on the definition. You can also calculate it based on the pressure here. So partial pressure for the water vapor and the saturation pressure at a given temperature. So as you can see here, we have an example. So you have a dew point temperature with a vapor pressure of 1.491, and then the saturation pressure is given for the same temperature as 3.169 kilopascal. If you find the ratio of this will give you a relative humidity value of 0.47. We can then convert this into percentage, which will give you a 47% of relative humidity. So most of our values of relative humidity are given in terms of percentage, or in terms of unity, the relative humidity ranges from 0 to 1, and in terms of percentage, it goes from 0 to 100%. Now, a point to note here, both specific humidity and relative humidity can be written as shown in this formula and also in this formula. So they are interconnected. So if you want to find your specific humidity based on the relative humidity given to you, you can use this formula. And if you want to find relative humidity based on the specific humidity given, then you can use this formula. And bear in mind, Pg is nothing but your saturation pressure at the given temperature. We will see in the examples later on how to use these formulas to calculate your saturation pressure and also your vapor pressure as shown in the formulas here. You also have the mass and enthalpy of mixtures, right? From the definition of relative humidity, the mass and enthalpy mixtures, you can express them as follow. So the total mass for atmospheric air can be given as mass of the dry air plus the mass of water vapor. If you factorize it to mass of dry air, this will result into this formula, and based on the definition earlier, we know mass of water vapor divided by mass of dry air will result in your specific humidity. So total mass of the atmospheric air can be written either in this formula, or you can calculate it based on this formula where ma is your mass of dry air. So this is the enthalpy. So the enthalpy, you can use the same relationships again, right? And then if you change your enthalpies, right, for your dry air and your moisture, so this will result in this formula. And then if you cancel out the dry air mass with this, that will result with HA, and then this MV over MA is nothing but your omega, so that will give you omega here, and this is your enthalpy of water vapor. So that will result in this formula. This is the enthalpy. So you can use the enthalpy of mixture to calculate out the enthalpy for problems related to air conditioning, and this is the associated unit. The unit is nothing but kilojoule per kilogram dry air. Okay, so this formula can also be equated to this formula. Again, bear in mind the temperatures here are in degree Celsius. So we will see how to use these formulas later in the examples in our next subsequent presentation. Now we also have another parameter that you need to understand. This is called dew point temperature. Now, if you live in a humid area or humid country like Malaysia, you are probably used to walking up most summer mornings and finding the grass wet. Why? You know it did not rain in the night before. So what happened? So now, even if it's not raining, but in the morning when you start walking over the grass is wet. So how is that possible? Now, the excess moisture in the air during the night simply condensed on the cool surfaces of the grass, forming what we call dew. Dew is also known as embun in Malay. So you will see that we have this dew formation of grass early in the morning, and this is formed because of this dew point temperature, right? So in summer, a considerable amount of water vaporizes during the day, right? Just like what happens in Malaysia. As the temperature falls during the night, so does the moisture capacity of the air. So this moisture capacity is the maximum amount of moisture the air can hold. So after a while, the moisture capacity of air equals to its moisture content. At this point, your air is saturated and its relative humidity is almost 100%. Any drop in this temperature will result in condensation of some of this moisture, and this is the beginning of dew formation that you see on the grass. So the dew point temperature, if you look at it, is defined as the temperature at which condensation begins when the air is cooled at constant pressure. All right, in other words, dew point temperature is the saturation temperature of water corresponding to the vapor pressure. So this you can see here on a TS diagram here. So on the TS diagram, as the air cools at constant pressure, so as the air cools at a constant pressure, the vapor pressure remains constant, right? So the vapor pressure remains constant. Therefore, the vapor in air state 1, right, undergoes a constant pressure cooling process until it strikes the saturated vapor line at state 2. The temperature at this point is called dew point temperature. And if the temperature drops any further, some vapor will then condense out. Right? As a result, the amount of vapor in the air decreases, which results in decrease of PV. So the air remains saturated during the condensation process and thus follows a path of 100% relative humidity. So the ordinary temperature and the dew point temperature of saturated air are identical, right? So now you may have noticed this if you look at this diagram, right? So when you buy a cold drink from uh, any canteen on a hot and humid day, you will see that there are dews forming on the outer surface of the glass. So the formation of dew on the outer surface indicates that the temperature of the drink is below the dew point temperature of the surrounding air. Right? So this is the information of dew point temperature. So we will be using this parameter again for our calculation later on. Now we also have dry bulb and wet bulb temperature. Now if you look at the thermometers here, right? So let's read this. So we have wet bulb temperature is read from wet bulb thermometer, which is an ordinary liquid in glass thermometer whose bulb is enclosed by wick moistened with air. Now if you look at this set of thermometers, this is called sling thermometer, hygrometer. So you have two thermometers, right? So one thermometer at the bulb here is exposed to air. Another thermometer here is covered with a wet wick, right? So in other words, you can also have wet cloth. So what happens is, so this thermometer will read the reading as it is of the surrounding air. So the temperature of the surrounding air will be illustrated here. Now the temperature of this thermometer will be lower than the temperature of the dry bulb thermometer. So you call this as dry bulb thermometer because there's nothing covering it, is dry. This is called wet bulb thermometer because the bulb here is covered with a wet wick. So you call this a wet bulb thermometer. Now the temperature here is the temperature of the surrounding. Now what do you think is the temperature for the wet bulb thermometer? The wet bulb thermometer will show a lower temperature compared to the dry bulb thermometer. The reason for this is when you cover the bulb with a wet cloth or a wet wick, some of the heat is lost to the surrounding by means of evaporation. So remember, this wick is wet and surrounding you have air. So part of the moisture from this wet wick will tend to evaporate into the air surrounding it. So when the water vapor evaporates, the temperature surrounding the bulb will drop, and it depends on how much evaporation is taking place. If the humidity of the surrounding air is low, then you will have very high evaporation. If the humidity of the surrounding air is high, the evaporation is lower, and as a result of that, the temperature drop will be lower. So by comparing these two temperatures on the thermometer, then you can actually measure the humidity level. So that is the basic science behind it, on how to measure the humidity level. So this is a sling hygrometer, but in today's world, right? So what we have is advances in electronics has made it possible to measure humidity directly in a fast and reliable way. So you don't see this much you see a lot of these electronic devices. So it appears that a sling cyclometer and wet wick thermometer are about to become things of the past. So this is becoming things of the past. Today you have handheld electronic humidity measurement devices. So you have this handheld, or you can also put it over the wall. And the measurement here is actually based on the capacitance change in a thin polymer film as it absorbs water vapor. And the device is capable of sensing and digitally displaying the relative humidity within 1% of accuracy. So that is the modern device that we have nowadays. So this was the earlier devices that is becoming almost extinct. So you can find this in a lot of museums nowadays. So we are using a lot of these digital devices to measure the humidity level. Now let's look at some sample problems first before we move into our next section. So here we have a 5 meter by 5 meter by 3 meter room which contains the air water vapor mixture at 25 degrees Celsius and 100 kPa. Now when you read this 100 kPa is the total pressure, all right, and the relative humidity phi is given at 75%. You are asked to determine the partial pressure of dry air, the specific humidity, the enthalpy per unit mass, the masses of dry air and water vapor in the room, and the dew point temperature. So how are we going to do that? So we have done all the formulas earlier. So now we will see how to use those formulas in order to get all the values from A to E. Now I've prepared a skeleton for your solution here. We will discuss the skeleton of the solution, but I want you to do all the whole problem again on your own based on the explanation given. So let's look at the solution here. So this is the skeleton that I've provided you. So look at the assumptions. So the assumption is the dry air and the water vapor in the room are considered as ideal gases. This is very important. Now we need to find the properties. So we need to look at the CP. So how do we get the value of CP here? So we will need to go to table A2 for your property table and charts. All right. So this can be found at page 909 for the property table and charts that I've shared with you. So you can go to the uh, row that shows you air, and you can easily find what is the value of CP here, which is shown as 1.005. So that is obtained from table A to A. Now the uh, temperature given to you is 25 degrees Celsius. So we need to find what is the saturation pressure for the moisture in the air at 25 degrees Celsius. By the way, please correct this. This is not T saturation. This is supposed to be P saturation. So this one is supposed to be P saturation, not T saturation. So you correct this. So this is P saturation, not uh, T saturation. So P saturation here at 25 degrees C, you will need to go to table A4, which shows you the saturated water temperature table. So you go to the temperature which gives you 25 degrees C, and then you will see that your saturation pressure is 3.1698 kilopascal. And from the same table, you can also find the enthalpy for saturated vapor. So at 25 degrees C, the enthalpy for saturated vapor is 2546.5. Now these are the values for the water vapor. P saturation for water vapor, and this is the enthalpy for water vapor, all right, in the air. So then we go to the first part of the solution. So as you can see here, we have done our Dalton law. So for Dalton law, we have total pressure. Total pressure is given as partial pressure of air, dry air, plus partial pressure of water vapor. Right, so this is the formula given to you based on Dalton's law. So if you rearrange, you will see that the partial pressure of air, dry air, is this partial pressure of dry air is equals to your total pressure minus the partial pressure of water vapor. Right, so you can also, because this is the first formula that you can obtain from Dalton's law, you can also find your partial pressure of water vapor based on the definition of uh, humidity ratio or relative humidity. So that is PV over PG. So we know our PG is the P saturation at 25 degrees C. So this value is given to you. So multiply with that. That will give you the partial pressure of water vapor here. We know what is the total pressure. You minus these two, that will give you your partial pressure of your dry air. So please do this. So skeleton is there, you should be able to obtain the values. Now we go to the specific humidity of air. So we will use this equation. So we have all the parameters needed. We have the partial pressure of water vapor, which we have obtained from here, and we can use the total pressure which is given in the question, and partial pressure of water vapor, again the same value, multiply it, use this formula, and that will give you the value of specific humidity. And remember, the unit here is kilogram of H2O divided by kilogram of dry air. Now the enthalpy, again based on this formula, right? So we will use this part. So we have Cp. Cp is given here 1.005. And what about T? Temperature is in 25 degrees C. So use 25 degrees C. Omega is obtained from here. And Hg is again given here, which we have found from table A4 earlier. So substitute it, then that will give you the value of H. Right? So the enthalpy of water vapor could also be determined from the earlier equation. If you want, you can find it from the equation that we've discussed earlier, and you will see that this is very much identical with the table A4 that we have here. So give it a try, use the formula that we've discussed earlier, see that you are able to get this value from the formula, right? And you will see that they are almost identical. Now to find the mass of dry air and mass of water vapor, we will first need to find out the volume. So the volume of the room, as you can see, the length, width, and the height of the room is given. So you can find the volume of the room, right? And then if you still remember the formula, P V, right, equals to M R T. Right, so from here you can rearrange this formula so that you can find what is the mass. So we are going to find the mass of dry air and mass of water vapor. So for mass of dry air, we have the partial pressure of, which is given here, partial pressure of dry air. Volume is same as this because all three occupies the same volume. So we will use the same answer that you've obtained from here, and the value for R can be obtained from the table and charts. All right, so you can find the gas constant. So this is given here. All right, so you can use that, and the temperature. So substitute it, and you should be able to get the value that you are looking for. And my question to you now is, what will be the unit for temperature here? So are you going to use Kelvin or are you going to use degree C here? So the unit here, so unit for this should be in Kelvin, not in degree C. So please note here, for this formula, the unit for temperature must be in Kelvin, not in degree C. So you've got to convert this 25 degrees C into Kelvin in order to substitute here. Now repeat the same thing for the mass of water vapor. So you know PV, so PV is given here. So this is our PV. So use that value. V volume is the same, R is again the same value that you have, and then T is the same, and you should be able to get what you call that, the mass of water vapor. Now you have to be very careful. The R value here for water vapor is different than the R value that you have here for air. So for air you can use 0.287, which is given here. Now it's your job to find out what is the R value for the gas constant value for the water vapor. All right. So just to let you know, the R value for water vapor is 0.4615. So learn and go and find out where to find this value from the property table and charts. All right. So then once you've got that, then you can use this formula. You can either find your mass flow rate, mass of water vapor using this formula, or you can also determine it by using this formula here, which is shown at the bottom. So that is the skeleton solution for example that we asked earlier. Now let's look at our next example. So this is an example involving dry bulb and wet bulb temperature. So this is a problem based on 6.4. So you have atmospheric air at 30 degrees C, and the total pressure given to you is 100 kilopascal. Dew point temperature given to you as 20 degrees C. So you are asked to determine these three parameters. So the first one is the relative humidity. Second one is the humidity ratio, or also known as specific humidity. And the third one is the enthalpy of mixture per mass of dry air. Now let's look at the solution. So in order to find the relative humidity, all you need to do is you use this formula, right, for the relative humidity. For that we have to find these two parameters, right, pressure PV and PG. PG is nothing but your P saturation at 30 degrees C, which you can find from the table easily, right? And this is for dew point or 20 degrees C, right? So you can find the P saturation at 20 degrees C, and this is easily found from the table here, right? So P saturation at 30 degrees C, P saturation at 20 degrees C, you can refer to table A4. That will give you the values of this easily, and you will be able to find what is the relative humidity, right? Next, to find the specific humidity. To find specific humidity, you will need to use this formula. So we know what is the total pressure. Our total pressure is 100 kPa. We've already found our PV, all right? So substitute the values here, and that will give you the humidity ratio. All right, so that is done for part B. And then for part C, you are required to find the enthalpy. Again, enthalpy, we will use this formula. All right, so you can find Cp. Cp is again same as what we've discussed, 1.005. You have the temperature given to you, all right, and then use the temperature again in degree C. Substitute it into this equation because omega is also known. So once you substitute it, you should be able to get what is the value for your H. So that is how you solve problem 6.4. Make sure you do it on your own. I've provided you with the skeleton. You should be able to solve it on your own. Now this is problem 6.5, right? So this problem 6.5 is based on a room which contains air at 20 degrees C and total pressure of 98 kilopascal, and a relative humidity of 85% is given. So you are asked to calculate the partial pressure of dry air, the specific humidity of the air, and the enthalpy per unit mass of dry air. So let's look at the skeleton again. So you are given the total pressure, so we can use this formula. We want to find the partial pressure of dry air. So in order to find that, we need to know what is the partial pressure of water vapor. So we find what is our saturation pressure at 20 degrees C, all right? We substitute it into this equation because we know the relative humidity. Point to note here, this is given in percentage, 85%, but when you substitute here, you must convert this percentage to 0.85. So you will have 0.85 multiply with the whatever value that you find from here. that will give you your PV. So substitute PV here. Total pressure is given as 98 kilopascal, and you should be able to find what is your partial pressure of dry air. That's easy. Then to find specific humidity, again we have both these parameters. Substitute it into this equation of your specific humidity, and you will be able to find your specific humidity. And bear in mind, this is the unit, kilogram H2O over kilogram dry air. And similarly, you can also find the enthalpy per unit mass of dry air by using this formula. So give it a try, see what you get for the enthalpy, and please practice this because it will be important for your assignments and exams later on as well.
Most air conditioning processes can be modeled as steady flow processes, and thus the mass balance relation as shown here, right, uh, can be expressed for dry air and water, right? So here we have energy balance applied to every section of air conditioning given to you in this formula, right? So what we're going to do here is we're going to disregard the kinetic and potential energy changes, right? So the steady flow energy balance will then change, where you'll have the heat transfer, the amount of work done to the system, right? And then this will be the mass that is moving into the system multiplied with the enthalpy. So these two parts are ignored, and you will have balance equals to this plus W out, and the mass balance, right, for the mass leaving the system multiply with enthalpy. So again, this kinetic portion and the potential portion will be neglected. This is the results that we get for the mass and energy balance. So conservation of mass for the steady flow control volume will result in the total mass that goes into a system is actually equal to the total mass that exits the system. So here conservation of mass is applied. So for dry air, the amount of dry air entering a system in an air conditioning is actually equal to the amount of dry air that exits. So that will give you the total amount of dry air that you have, right? So for water vapor, the amount of water vapor in is equals to the water vapor out, right? So again, mass and energy balance. So if you want to change this mass of water vapor in terms of mass of dry air, then you will need to multiply the mass of dry air with specific humidity ratio that is given here. Right, so these are the mass and energy balance equations that you will be using extensively throughout the analysis for air conditioning problems.
Okay, so we will now begin with our next part, which is the psychrometric chart. So as you can see here, we have the psychrometric chart shown almost like a shoe design, right? We will see how it looks like, right? So for a given fixed total air vapor pressure, the properties of the mixture are given in graphical form on a psychrometric chart. So you can see that the state of the atmospheric air at a specified pressure is completely specified by two independent intensive properties. So you can have any of these two properties. You can use that to specify the condition of the specified pressure or the air properties that you have. The rest of the properties can be calculated easily from the previous relations, right? So you've done that in the previous sections. The sizing of a typical air conditioning system involves numerous such calculations, which may eventually be very cumbersome for most of the engineers, right? So in order to avoid that, so there is a clear motivation to computerize calculations or to do these calculations once and to present the data in the form of easily readable charts. So such charts we call them as psychrometric chart, right? So you can actually represent the air conditioning processes on a psychrometric chart easily. So let's say this is your reference point. If you want to move towards cooling, so this reference point will then move towards the left as shown here. So if you have your reference point here again, if you want to do a heating in terms of air conditioning processes, then this point will move towards the right as shown here. For humidifying, it will move towards up. For dehumidifying, it will move towards down. So it becomes a very valuable aid in visualizing the air conditioning processes. You can also do the cooling and dehumidifying, where the direction of movement will be towards this direction, and heating and humidifying will move in this direction, right? So there are many parameters that you can obtain. You can have the dry bulb temperature, you can have wet bulb temperature, you can have the enthalpy lines, you can have the specific volume line, you can have the specific humidity property obtained from the psychrometric chart, right? You can also have the relative humidity line. So the actual psychrometric chart looks like what is going to be presented in our next slide. So this is the psychrometric chart. This is how it looks like. So I would like to bring your attention to the first important term here. If you want to use this psychrometric chart, you must make sure that your pressure is 101.325 kilopascal. Any pressure besides this pressure, you will not be able to use the psychrometric chart. 100 kilopascal is not 101.325 kilopascal. For 100 kilopascal, you will have no choice but to use the earlier equations. But if your pressure is at 1 atm or 101.325 kilopascal, then you can freely use the psychrometric chart to solve problems related to air conditioning processes. So as you can see from here, you have the psychrometric chart shown as what we've discussed earlier in a shoe form. All right, so on the y-axis here, you have all the values for humidity ratio. So this humidity ratio, bear in mind, the unit is in grams moisture per kilogram dry air. We mostly use values in kilograms moisture per kilogram dry air, but in this chart the value for humidity ratio is given as grams moisture per kilogram dry air. So if you read 22, so the value is 22 grams moisture per kilogram dry air. So you will need to convert this into kilogram moisture per kilogram dry air for your further calculations. So that is the value that you have on your y-axis here. On your x-axis, you have dry bulb temperature in degrees C. So you have 0, 10, 20, 30, 40, and 50. You have your wet bulb temperature shown here on the dotted lines here, right? So these are the wet bulb temperatures. So this is the wet bulb temperature at 30 degrees C. So as you go down, this is the wet bulb temperature is 25 degrees C. Wet bulb temperature of 15 degrees C is shown here. 10 degrees C is shown here. 5 degrees C is shown here, and so on. Then you also have lines representing your relative humidity. So this is the line representing 10% relative humidity. You have 20% relative humidity, 30, 40, 50, 60, 70, 80, 90. And the last line here represents the relative humidity of 100%. So saturation is also known as relative humidity of 100%. Right? So you also have saturation temperature given here. The other property that you can get from psychrometric chart is your specific volume. So those lines are represented by this darkened line here. So you have 0.94. As you go down, it reduces to 0.92. This is 0.91, 0. I'm sorry, 0.94, 0.93, 0.92, 0.91, 0.90, and so on. All right, so those are the lines for specific volume, and you will see that the unit is volume cubic meter per kilogram, meter cube per kilogram of dry air. So you can also find the enthalpy, so based on the scale given here, right? So these are the parameters that you can actually obtain from a psychrometric chart. And remember, again, we can only use the psychrometric chart when the pressure is 101.325. Nothing more, nothing less than this. Anything more than this or anything less than this value, you will need to use the formulas as what we've discussed earlier. So right, so even 100 kilopascal you cannot use the psychromatic chart. It has to be 101.325 kilopascal or 1 atm. So now let's look at this question here. So you have how to use psychromatic chart. So we will then learn how to use the psychromatic chart based on this question. So you have dry and wet bulb temperature of atmospheric air at 1 atm. This is very important. So the moment they say is 1 atm or 101.325 kilopascal, you know automatically you can use the psychromatic chart. So the pressure are measured with sling psychrometer and determined to be 25 degrees C and 15 degrees C respectively. So you have dry bulb temperature 25, wet bulb temperature 15. So these are the two parameters given. So in the psychromatic chart you have more than two parameters. So in order to find other parameters you need a minimum of two parameters. So those two parameters are given to you, right? So based on these two parameters, how are you going to use the psychrometric chart to find specific humidity, relative humidity, and enthalpy of the air for this problem? So now let's look at the solution. So this is the psychrometric chart. Now remember, based on the question, you are given 25 degrees C as the dry bulb temperature, 15 degrees C as the wet bulb temperature, and the pressure is given as 101.325, which corresponds to this, and we are very confident that we can use psychrometric chart because the pressure corresponds to the pressure that is stated here. So now let's start. So we have the dry bulb temperature 25 degrees C. So you can see here this is the axis for the dry bulb temperature. So you need to find where is 25 degrees C. So we have 20 degrees C here, we have 30 degrees C here. Obviously 25 degrees C is somewhere in between. So what you need to do is you need to draw a line. Alright, so draw a line at 25 degrees C to represent this value. So this is the line that I've drawn to represent the value for 25 degrees C. Now we need to find what is the wet bulb temperature. So the wet bulb temperature line is shown here, the dotted lines. So we have 30 degrees C here, we have 25 degrees C here, but we need to find where is the 15 degrees C. So if you find the 15 degrees C, the 15 degrees C line for wet bulb temperature is shown here. So it is inclined as the dotted lines here. So again we draw another line there. So based on these two parameters, you will find an intersection point here. So this intersection point is very important because based on this intersection point, we will find the other parameters that we want. So the first parameter that we are looking for is the specific humidity. So the specific humidity is given here. Right, so this is the specific humidity. What you need to do is from this intersection point, you need to extrapolate a straight line that intersects with this axis in order to obtain your humidity ratio. So you draw a line, so it intersects at this point, you read what is the value here, and that becomes your specific humidity value, right? So the next point that we want to find is your enthalpy. So enthalpy, you draw a line which is parallel to these lines and it intersects to this point here. Based on the scale given, then you can find what is the enthalpy that you want. And next is you want to find your relative humidity. To find relative humidity, it is between 30% to 40%. Now you've got to estimate, draw a line which is parallel to these two lines. All right, so this is the blue line that I've drawn. So this is parallel, and then you estimate between 30 to 40 here on your appropriate scales that you can find what is the value of this line. So it seems like it is between 33 and 34%. All right, so then you can use the psychrometric chart here as what we've discussed to solve the problem that is given to you. All right, so I hope it helps. The illustration helps you to find the values. Now let's look at another example. So this is again based on psychrometric chart. So this is a room. Again, the most important parameter if you want to know whether you can use the psychrometric chart or not is the pressure. So the pressure here is at 1 atm, so we can use the psychrometric chart easily. So we need two parameters in order to use the psychrometric chart. So what is given to you is the dry bulb temperature at 35 and the relative humidity is given to you at 40%. So use the psychometric chart to find these 5 parameters: specific humidity, enthalpy, wet bulb temperature, dew point temperature, and the specific volume of the air. Now let's look how to find that. So we have our psychometric chart. So we want to now find where is our temperature at 35 degrees C. So dry bulb temperature is given here. So 35 degrees C, we draw a line straight up, vertical line at 35 degrees C. So that is to represent our dry bulb temperature. Then we find what is our relative humidity, 40%. So we have, these are the relative humidity lines. So 10% is here, 20, 30, 40. So this is the line that represents 40% relative humidity. So that will give you an intersection point here. So that is your intersection point as shown as the blue dot there. Now based on this, we want to find what is our specific humidity. So to do that, from this intersection point, you pull a line straight horizontally so that you cut this axis, y-axis, to find the value of your specific humidity. So wherever you find the intersection here, so based on the scale given here, you find out what is the value. That will be the value of your specific humidity. Next, to find the enthalpy, we draw a line again parallel to these lines until we intersect this scale here, and then the value at this particular point based on the scale given to you, that will be the enthalpy of that problem. Now to find wet bulb temperature, we need to draw a line parallel to the wet bulb lines here. So to do that, so first we will find the dew point temperature again. To find the dew point temperature, all you need to do is you draw a straight line, horizontal line, until it intersects to the saturation temperature line here. So the line that cuts the scale here will give you the dew point temperature. All right. So you can find the dew point temperature based on that. And then this is your specific volume of the air. Specific volume of the air, you see that these are the lines that represents the specific volume of the air. So you can use the specific volume of the air based on this 0.92, and then you have 0.91, 0.90, and then here we have 0.89. So between 0.89 and 0.90, you can divide the scales and find out what is your specific volume of the air. Now remember, we have not found the wet bulb temperature line. So the wet bulb temperature line is the same as the enthalpy line that we have drawn earlier, right? So you can estimate what is your wet bulb temperature. You see that this is your wet bulb temperature that you have here, which is 25, and here is 20, and then there is an increment of 1. So this line here is on the wet bulb temperature of this line. So you will see that your wet bulb temperature is 24 degrees Celsius. So with that, you are able to find all the 5 parameters that you need to solve the problems for problem 6.7. Right? So hope the illustration helps you. So find all the values on your own, learn how to use the psychometric chart. Right? So it is very important for you to know how to find the values based on psychometric chart, because it will be very helpful for you in the exams and also for your assignments later on, and not forgetting your time. Right? So that was on your psychometric chart. So now we have air conditioning processes. So again, just to recap, air conditioning processes include simple heating. So when you heat up something, you raise the temperature. Simple cooling is just by lowering the temperature. Humidifying is where you add the moisture. Dehumidifying is removing moisture. So these are the typical air conditioning processes that you have. Sometimes you can combine 1, 2 or more of these processes, all right, to bring the air to the desired temperature and humidity level. Sometimes you need to have heating with humidifying. Sometimes you need to have cooling with dehumidifying. So you can combine these processes together. So these are the various air conditioning processes as what we've discussed earlier. So cooling, heating, humidifying, dehumidifying, or you can combine them, cooling and dehumidifying, heating and humidifying. Now let's look at one of the simple heating and cooling processes. So for simple heating and cooling processes, you will notice your specific humidity is always constant, right? So we have many residential heating systems consist of a stove, a heat pump, or an electric resistance heater. So this is your heater or heating coil. The air in this system is heated by circulating it through a duct that contains the tubing for the hot gases or electric resistance wire. Now, if you want to do cooling, you can do the same setup, but instead of having heat here, you can then pass the air over some coils through which a refrigerant or chilled water flows, right? So heating and cooling appears as a horizontal line since no moisture is added or removed from the air. So this statement, you can refer to the psychometric chart here. For an example, if you want to cool the stream of air from 30 degrees Celsius to 12 degrees Celsius, you will see that the line moves in a horizontal direction because you are not humidifying or dehumidifying anything. So it will move from point 1 to point 2. Because there is a change in temperature, your relative humidity values will also change. But since the line is moving in a horizontal direction, your specific humidity value is not changing, and that is why your omega is constant, right? So the formulas that we have here: dry air mass, so conservation of mass, right? The mass that is moving in the first position is equal to the mass that is going into the second position, which is the total mass, right? So since it's a horizontal line on a psychometric chart, your specific humidity will not change. And then because you are either adding heat or removing heat, your enthalpies will change, and based on that enthalpy change, you can then find out your energy balance. All right, so these are the formulas that you can have for simple heating and cooling, and you can also illustrate it easily on a psychometric chart here. All right.
Here we have uh, an air conditioning process. What we're going to do here is we're going to talk about air conditioning process involves simple heating. So what is simple heating? So if you look at this diagram here, for simple heating, you will have a heating coil which supplies heat to the air conditioning system, and then you will have your air that needs to be treated at state 1 passing through this air conditioning process, and then as a result of that you will reach state 2. Now because this is heating, your temperature will go from T1 to T2, where T2 is higher than T1. So the moment you have that involves heating. But because you are not adding or removing any moisture, in other words, there is no humidification or dehumidification processes, your omega remains the same, right? But since it involves change in temperature from state 1 to state 2, your relative humidity will change as shown here, right? So so based on this, so the conservation of mass equations for heating or cooling process that involves no humidification or dehumidification reduces to you will see that your m dot a1 and m dot a2 is same, and that relates to the total mass of dry air that is going from state 1 to state 2, right? So if you neglect any fan work that may be present, conservation of energy equation, so we neglect the kinetic and potential part, so there is no energy leaving out of the system, no pumping work done, and out, in and out. So if you simplify this equation, you will get this equation related to simple heating for air conditioning processes. So the Q in through the heating coil is given by m dot a h2 minus h1. Right. So that is for simple heating. We also have simple cooling. So in simple cooling, similar to heating, but heating is where we supply heat to the air conditioning processes. In cooling, we will absorb heat out of the system. So again, let's look at this control volume here. So what you have here is, instead of supplying heating coil, you will supply a cooling coil. So this cooling coil will then absorb the heat out of the system. So as a result of that, you have this statement here for Q out not cancel, but we don't add any energy into the system. So you have to cancel this out. No work done by any pump or system. So you have the mass flow rate times with the H at state 1. So kinetic and potential is neglected for both the parts. All right. So there's no work done by any of the system for the out state 2 as well. All right. So because it involves cooling, your temperature T2 at state 2 will be lower than T1. Now again, no dehumidification and humidification. As a result of that, your specific humidity remains same. But your temperatures are not similar for state 1 and state 2. Your relative humidity will also not be similar. So instead of looking for Q in as what we've discussed in simple heating, for simple cooling, you will calculate out what is your Q out, amount of heat that you take out from the system, m dot A H1 minus H2.
Then you have heating with humidification. So now heating is just heating. So what you have, a stream of air coming from point 1 which is exposed to heating coils. So it will then heat up. As a result of that, your temperature will rise. So for an example here, we have point 1 to point 2. So point 1 is 10 degrees Celsius. You want to heat it up to 22 degrees Celsius. So then you will pass this stream of air through some heating coil. As a result of that, your temperature will raise up to 22. As from point 1 to point 2, you are not adding any moisture or removing any moisture. So as a result of that, this line is horizontal. So and due to that, your omega remains same. So omega 1 is equals to omega 2. So this happens at the heating section. Now because we have heating with humidification, humidification here means you are adding moisture. So you can either spray some water vapor into the system as shown here with the help of a humidifier. So when your air moves from point 2, this is heated, and then it goes to point 3, you are adding moisture. So when you add moisture, your specific humidity changes and the line on the psychometric chart moves in this direction. So it goes from point 2 to point 3, and you will see that there is an increase in your specific humidity from this level to this level. So and that is the reason why you have omega 3 more than omega 2 here. And these are the formulas that you use for dry air mass balance. You will see that the conservation of mass balance is applied here. The amount of mass that you have 0.1 is conserved at 0.2 and is also conserved at 0.3. So the total mass of air is conserved, so they remain the same. Now if you want to find the water mass balance, we will see that the amount of water that is available at 0.1 and amount of water that is available, water moisture in the air available at 0.2 is same. So that results in omega 1 equals to omega 2. So energy balance at 0.1 and 0.2 is given by this formula again. So this is for the heating section. Now, since we are having a humidifier, this humidifier is adding some water moisture into the air, and that is given by this formula. So amount of air at 0.2 times with omega 2, that gives you this relationship, plus with the amount of water vapor that are being introduced by the humidifier equals to this m dot A3 times omega 3. So if you want to know how much water vapor is being introduced by the humidifier, you can rearrange this, and that will give you m dot A omega 3 minus omega 2. And this will give you the amount of water moisture that is being injected into the air conditioning process. So that is for heating and humidification. We also have the next part, which is the cooling with dehumidification. In cooling with dehumidification, as you can see here, we are reducing the temperature. So when you reduce the temperature, right, so again the point 1 moves towards the left of the psychometric chart until your relative humidity becomes 100%, or the air reaches very high humidity that it becomes saturated. So the other meaning for saturated level is humidity is at 100%. So you can see here specific humidity of air remains constant during a simple cooling process. You can see here specific humidity is constant, right? But its relative humidity increases. So from 80% it has increased to 100%. If the relative humidity reaches undesirably high levels, it may be necessary to remove some moisture from the air, that is to dehumidify it, and this is what happens in our air conditioning processes. All right, so this requires cooling the air below its dew point temperature. So again the dry air mass balance is same, right? Whatever mass balance, because you are losing water, so we want to know how much water is dehumidified, the condensate removal. You can use this formula to calculate, right? And then the energy balance is given by this formula. You can calculate out how much heat is uh, removed from the cooling section of these cooling coils by using m dot h1 minus h2, which are the enthalpy differences between point 1 and point 2. And remember, you must also minus from the vapor that we are losing through the condensate removal. So that will be the equation used for the energy balance for cooling with dehumidification. Right. So now we can look at sample problem 6.8. So here we have a heating section consists of a 38 cm diameter duct that houses a 4 kilowatt electrical resistance heater. The air enters the heating section at 1 atm, again 1 atm. You can use psychometric chart, 10 degrees Celsius and 40% relative humidity at a velocity of 8 meters per second. So determine the exit temperature, exit relative humidity of the air, and the exit velocity. So this is the skeleton again. So we use these assumptions. This is a steady flow process, and thus the mass flow rate of dry air remains constant throughout the entire process. So the mass from point 1 to point 2 is the same. Dry air and water vapor are considered as ideal gases. Kinetic and potential energy changes are negligible, right? So for the analysis, the amount of moisture in the air remains constant, right? So omega 1 is equals to omega 2 as it flows through the heating. So this is only heating, no humidification, no dehumidification, right? Inlet state of air is completely specified, and we have 1 atm, so you can use your psychometric chart. So go to point number 1. Point number 1, you have 10 degrees C dry bulb temperature, 40% relative humidity. Based on these two parameters, find what is your H1, omega 1 and specific volume, right? So this can be obtained from your psychometric chart, and note that omega 1 is equals to omega 2. Then you can find your mass flow rate. So m dot is equals to rho AV. So based on the formula, so this is 1 over specific volume is your rho. All right, make sure you know that. And your volume, you can calculate out your volume. I'm sorry, this is not volume, this is your velocity. So 8 meters per second is your velocity, and then this is your cross sectional area. So make sure you know how to calculate your cross-sectional area for a 38 cm diameter, pi d squared over 4, but make sure you change cm to meter as well. So that will give you the mass flow rate in kilogram per second. So Q in is given to you. Q in is 4 kilowatt. All right. So H1 is known. So m dot A is known from here. So you should be able to find what is your H2 easily. So now you have your omega 2. All right, you have your H2. So again, 2 points are given for point number 2, and then go back to your psychometric chart, find what is your dry bulb temperature at T2, relative humidity and specific volume. All right, so once you've got that, the exit velocity again based on your mass flow rate. So this is your volume flow rate divided by specific volume, should be equal to your volume flow rate at 0.2 divided by specific volume. So you rearrange it into this formula, find your V2 based on this formula, and that will give you the exit velocity. right? So the skeleton is given to you. You should be able to solve this problem easily, find out the values here, all right? So if there are any problems, we will discuss it in the class. So now we have another problem. So you have air that enters a 40 cm diameter cooling section. Now you have a cooling section at 1 atm again, 32 degrees C and 30% relative humidity at a velocity of 18 meters per second. Heat is removed from the air at a rate of 1200 kilojoule per minute. You are asked to determine the exit temperature, exit relative humidity of the air, and the exit velocity. So let's see how to do this. So again, assumptions are same as the previous example. So m dot a1 equals to m dot a2 equals to m dot a. So because it's only single duct, so the mass flow rate is considered to be the same for both the points. And then the amount of moisture remains same because it's a simple cooling. So omega 1 equals to omega 2. All right. So no humidification, no dehumidification. So the inlet state is given 32 degrees C and 30% relative humidity. So this is given to you at 0.1. So based on 0.1 parameters, 32 degrees C dry bulb temperature, 30% relative humidity, go to your psychrometric chart, find what is your H1, omega 1 and specific volume. So omega 1 equals to your omega 2. So similarly, you can also find your mass flow rate, rho AV. So rho is 1 over V1, which is your specific volume here. Velocity is given to you as 18. And your cross-sectional area can be found using this diameter, 40 cm diameter. Right? Change this to meter. Don't forget that. And then from the energy balance, you can see that negative Q out equals to m dot A H2 minus H1. So negative because you are absorbing the heat out. So you have the quantity negative here. All right. So this is given to you in kilojoule per minute. We need to change this to SI. So we will then change this to kilojoule per second by dividing this with 60. So that is how you change kilojoule per minute to kilojoule per second, because 1 minute is 60 seconds. So you divide this with 60, that will give you negative 1/200 divided by 60. Why negative? Because for cooling you are absorbing the heat out of the system. All right. So m dot A is given here. All right. H1 is known. Negative Q out is here. So you can find H2. So now for point number 2, you have H2. You have omega 2, which is similar to omega 1. So once you have these 2 points, you should be able to find what is T2, relative humidity at point number 2, and specific volume at point number 2. And then to find your velocity, we use back the same formula as discussed earlier. Should be able to get what is the velocity at point number 2. So give it a try, find the values, and you should be able to get all the values needed, all right, as explained in this presentation. Now we have the third example, sample problem 6.10. So again, you have air at 1 atm, 15 degrees C, 60% relative humidity. You are given a rate, volumetric rate, 2 meter cube per minute. Is first heated to 20 degrees C in a heating section and then humidified by introducing water vapor. The air leaves the humidifying section at 25 degrees C and 65% relative humidity. You are asked to determine the amount of steam added to the air and the amount of heat transferred to the air in the heating section. Now let's look at the skeleton of the solution here. So assumptions again, because it's a single duct, so your mass flow rate, conservation of mass is conserved, right? And then you have inlet conditions given to you, dry bulb temperature 15, relative humidity 60. So based on that, you should be able to find what is your H1 and omega 1. You are also given the exit conditions. So the exit conditions, dry bulb temperature is 25 and your relative humidity is 65. Now based on this, based on the exit conditions after the heating coil, right? So that is given to you. So you should be able to find what is your H3 and omega 3, right? So H3 and omega 3 are found based on this temperature and this relative humidity. So you have these 2 points, go to your psychrometric chart and that will give you your H3 and omega 3. right? So based on that, you will have all these values that you need, right? To find H2 is quite easy. Omega 1 is known, which is equals to your omega 2, and you also know that the temperature of dry bulb temperature is 20 degrees C at point 2. So use this temperature and use this omega, and you should be able to find what is your H2, right? So amount of moisture in the air remains constant as it flows from the heating section. From here to here, omega is same, right? But your omega changes from point 2 to point 3. So you have omega 3 and your omega 2. Find the difference in these two. So that will be the amount of steam added to the air in the heating section. So the delta omega, the difference between omega 3 and omega 2, is the amount of steam added to the air, right? And then to find the heat transfer, it is nothing but H2 minus H1. Right, so that is the heat transfer through the heating coil, and you find that heat transfer to the air in the heating section per unit mass of air is given as H2 minus H1. That will give you the answer in kilojoule per kilogram dry. So give it a try, get the values, skeleton is there, it should be easy. You should be able to get all the values that you need. So practice.
Now let's look at this problem. So for this problem, we have an air conditioning system to take in outdoor air at 10 degrees Celsius and 30% relative humidity at a steady rate of 45 meter cube per minute. So please bear in mind the units here. It's meter cube per minute. You might need to change this to meter cube per second. And to condition it to 25 degrees C, so from 10 degrees C, condition it to 25 degrees C and 60% relative humidity. So how are you going to change 30% relative humidity to 60% relative humidity? So you got to add in some moisture. So we will see that in a while. So the outdoor air is first heated to 22 degrees C. So from 10 degrees C, you are heating it up to 22 degrees C in the heating section, and then humidified. Humidified here means you are adding moisture. So how do you do that? It's by injection of hot steam. Now when you have hot steam, what's going to happen is when you inject hot steam for 22 degrees Celsius, what's going to happen is the temperature is going to go up because you are exposing this stream of air to steam. So as a result of that, as you can see, we have increased the temperature from 10 degrees C to 22 degrees C. But because you are injecting steam, this will further increase the temperature to 25 degrees C here. Right? So that is done in the humidifying section. Now assuming the entire process takes place at a pressure of 100 kilopascal. Now this is very important for you to understand. This is 100 kilopascal. This is not 1 atmosphere or not 101.325 kilopascal. So in other words, you can't use psychromatic chart to solve this problem. So for this problem, because the pressure is at 100 kPa, you will need to do it using the formulas. Right? We will see how to do that. You are asked to determine A, the rate of heat supply in the heating section, and B, the mass flow rate of the steam required in the humidifying section. So look at the chart here. So the process is represented with the help of these two diagrams here. So as mentioned, 10 degrees C, 30% relative humidity, volumetric flow rate given to you. It passes through a heating coil. As a result of that, your temperature increases to 22, and after this it passes through the humidifying section where a jet of steam is introduced to the air that is passing through. As a result of that, your temperature goes from 22 to 25 degrees C. So when it goes from 10 degrees C to 22 degrees C, there is no increase in your moisture, and that is why this line is horizontal. So meaning to say that your omega remains constant. Now once you have reached this point, point number 2 to point number 3, you will see that your omega is increasing. So this line here on the psychrometric chart shows you the omega value, specific humidity. You see that your specific humidity has increased from this point to this point, and this is because of the injection of steam into the stream of air, right? Now, I've mentioned to you we can use psychometric chart to obtain the values on the psychometric chart to solve this problem. But here we can use the psychometric chart to represent the process or whatever conditions that we have in the question that we are discussing. So this is just to illustrate to you what is happening, right? Because the pressure is at 100 kPa, we've got to use the equations. So this is what you have for energy balance at the heating section, right? So this is the energy balance at the heating section, so which I've described to you earlier. So you have that Q in, so amount of heat supplied into the stream, m dot A H2 minus H1. So you should be able to find what is H2 and H1, m dot A. And mass balance for water vapor, how much water vapor is actually introduced. You can use this relationship, m dot A omega 3, you find omega 3 minus the omega 2 that you have at state 2. And bear in mind omega 1 and omega 2, they have the same value because you are not introducing or extracting any moisture from state 1 to state 2. So now look at the skeleton of solution. So what you need to do is you got to solve this on your own. I have left some places here blank for you to fill up, right? So the assumption here is you have steady state flow process, thus the mass flow rate of the dry air remains constant during the entire process. So number two, your assumption is dry air and water vapor are ideal gases. And number three, the kinetic and potential energy changes are negligible. So we look for properties, constant pressure, specific heat of air at room temperature. So you go to table A2, we assume it to be ideal gas, specific heat. So we are using air. So our Cp is obtained from here. So you can substitute this value into the uh, empty space here that I've provided you so that you can fill up the blank. And then to get your gas constant, again you go to this table, you'll be able to get your gas constant 0.2870. The units are there, right? And saturation pressure of water. So for saturation pressure of water, you will need to go to table A4 and then go to temperature. This is temperature table. So you have both saturated water temperature table and pressure table, but we will refer to temperature table. You go to at this temperature, which is 10 degrees C, find what is the saturation pressure. So that will be the answer here, right? And at 25, what is the saturation pressure? Again, substitute it here. So the enthalpy of saturated water vapor, right? Saturated water vapor. So you got to find what is the saturated water vapor at 10 degrees C, right? And at 22 degrees C. So for 10 degrees C is easy. You should be able to find out easily from here. Now for 22 degrees C, you will see that you don't have the value for 22 degrees C. So you got to interpolate between 20 and 25 in order to find the value for enthalpy for saturated water vapor at 22 degrees C. So all that can be found from table A4 here, right? So based on the analysis, so what we have, omega 1 is equals to omega 2. I've already explained this to you. And then omega 3 is more than omega 2. So we need to find this, right? So dry air mass balance is given. Water mass balance is given here. And then the energy balance we've discussed is also presented as this, right? So point here, psychometric chart offers great convenience, we know that, right? However, its use is limited to specified pressure only, which is 1 atm or 101. This problem that we are discussing is not 1 atm, right? So we have to then use the formulas. These are the formulas that you'll be using, right? So you find the partial pressure of vapor, right? So relative humidity at 0.1 given, and then saturation pressure at 0.1 is nothing but your saturation pressure at 10 degrees C, which we have found. Substitute it, find the value here. Once you know partial pressure for your vapor, you know total pressure is given as 100 kPa minus from the partial pressure for vapor. That will give you the partial pressure for air. So using the PV equals to MRT, so you can find this specific volume for the air, right? and then this will give you the mass flow rate of air, right? So this is given in the equation. So based on whatever value that is given to you in the equation, but bear in mind that is per minute. Change it to per second if you want, or you want to remain it as per minute, but just be careful with your units. And next we go to our omega 1. You have all the values here, PV1, P1, PV1. Substitute, that will give you your omega 1. So the unit again is kilogram H2O per kilogram dry air, right? And with that, you go to this section where you find your H1 and H2 based on what we've discussed, and then bear in mind T1 and T2 should be in degree C. So once you've obtained all these values, substitute into these equations to get your Q in, substitute into this to get your omega 3, and m dot w, then you can use this formula. M dot a is known from here, omega 3 is found from here, omega 2 is equals to omega 1, right? So substitute all the parameters into this equation, and that will give you m dot w, right? So the result that you get from here, right, will actually tell you that it corresponds to a water requirement of close to 1 ton a day, which is quite significant. So if you want to cool down, if you want to increase the temperature and humidity of this problem, which is related to heating and humidification, right, you will need almost 1 ton of water, 1 ton of steam, right? So that is the solution for this question. So please do on your own. Skeleton is provided. I've purposely left out the solution so that you are able to do it on your own, because this type of you can either solve this using psychometric chart, which is the easier way, and this is the harder way, and you have no choice, but you need to know both the methods, the psychometric chart and also how to solve the problems using the formulas as what we've discussed in this example.
Another problem, we have air that enters a window air conditioner at 1 atm, 32 degrees C and 70% relative humidity at a rate of 2 meter cube per minute, and it leaves as saturated air at 15 degrees C. Part of the moisture in the air that condenses during the process is also removed at 15 degrees C. So you are asked to determine the rates of heat and moisture removal from the air. So this is the skeleton again. So this is cooling with dehumidification. Alright. So conservation of mass. So the inlet and exit states are given. So this is the inlet. So based on 32, dry bulb temperature, relative humidity 70%. So find what is your H1, omega 1 and specific volume from your psychometric chart. Exit conditions are also given, T2 and relative humidity 2, 15 degrees. Now this is saturated. So if it's saturated, the value for your relative humidity will be found right towards the edge of the psychometric chart, the last line for the relative humidity after 90%. So that will give you your H2 and omega 2. All right. So you must also find your enthalpy. All right. So liquid, saturated liquid at 15 degrees C, right? Because this condenses at 15 degrees C. So you must find saturated liquid at 15 degrees C from table A4. So find what is the enthalpy for that. And then this will give you, because you don't know what is the mass flow rate, but you are given a volume flow rate. So your volume flow rate divided by specific volume, which we have found from here, that will give you the mass flow rate that you want. Right, so with that you'll be able to find the mass flow rate. And now based on this equation, energy balance, you will be able to find what is the mass of condensate removal from the system. So omega 1 minus omega 2 times with the mass flow rate of the air, that will give you the water mass balance, amount of water that condenses out from the system. And the Q out, amount of heat that is absorbed by the cooling coils, is given by this formula again, right? M dot A H1 minus H2 minus the heat loss through the condensate removal. So this is the condensate removal, M dot W, which is found from here, and HW is this value that you found from table A4, and that will give you your Q out. All right, so please try this question. And the last one that we have here is your adiabatic mixing of air streams. So in many air conditioning applications, we have two different streams mixing in the adiabatic sections of the what do you call that mixing section as shown here. So you can have the return air from the confined space of the room coming in, and this is mixed with fresh air coming from the outside, because in very large buildings or most production and process plants and hospitals, we require that the conditioned air to be mixed with certain fraction of fresh air outside. So you have two ducts. One is carrying the return air from the room, and this is mixed with the outside fresh air in this mixing section. So once they are mixed, and then they are delivered again to the desired confined space, like in the hospital room or office building. So again, based on the mass balance, again, if you have mass coming in from 0.1, total mass from 0.2, if you add it up, that should be the total mass that is going in at 0.3. So for water vapor, again, so we will use this mass balance, and for the energy, again, it is shown as this mass balance here. All right, so on the psychometric chart, you can see that you have 0.1 and 0.2 here. So what it does is from 0.1, right, so this is cooled air coming in, and this is the fresh air at a higher temperature, and they are mixed, and you will get this particular property at point number 3, right? So based on this relationship that is shown here, you can then find out your ratio of mass flow rate of air coming in at 0.1 divided by mass flow rate of air coming in from 0.2. You can find the specific humidity or 0.3 based on the values that you've got at 0.1 and 0.2, and you can equate this, and you should be able to get your specific humidity at 0.3, and you can also equate this enthalpy relationship to this value here, the ratio, and you should be able to get what is the enthalpy at H3. Right, so this is for adiabatic mixing of air streams.
So sample problem for our next problem. So this is based on adiabatic mixing. So as you can see here, so we have stream 1, stream 2 mixed in this adiabatic section and then delivered as at state 3. So what we have is two streams mixed steadily and adiabatically. First stream enters at 32 degrees C, right, and 40% relative humidity at a rate of 20 meter cube per minute, while the second stream enters at 12 degrees C and 90% relative humidity at a rate of 25 meter cube per minute. Assuming that the mixing process occurs at a pressure of 90 kilopascal. So bear in mind this is 90 kilopascal, not at 1 atm. So you can't use psychometric chart here. You will have to do it using your equations. So you are asked to determine the specific humidity, relative humidity, the dry bulb temperature, and the volume flow rate of the mixture, which is this one, state 3. Right, so remember we've discussed this formula. So mass flow rate of dry air at 1 ratio to mass flow rate of dry air at 2, this ratio is actually equals to enthalpy at 0.2 minus enthalpy 0.3 divided by H3 minus H1, or it is also equals to omega 2 minus omega 3 divided by omega 3 minus omega 1. So what you can do is you can equate this to this first to find H3, or you can equate this to find omega 3. Once you know your omega 1 and omega 2 and H1 and H2, you can easily find H3 and omega 3 by using this relationship. Now let's look at the solution. This solution here is again in the form of skeleton. So these are the information given to you: 32 degrees C, 40% relative humidity, volumetric flow rate of 0.1 given. Similarly at 0.2, your temperature, relative humidity, and volumetric flow rate is given. So they are mixed here at 90 kPa, and you are asked to find all these values. right? So again, similarly, we can't use psychrometric chart because of the pressure here. It's not 1 atm. So we will need to find this partial pressure of water vapor. So again, using the same formula here, relative humidity times with the saturation pressure at point 1, which is at 32 degrees C. Refer back to your psychrometric, what you call that, property table charts, right? And you'll be able to get this value, substitute it here, because P1 is known as 90 kilopascal, and you should be able to get your partial pressure for the air at point number 1. And that will give you a specific volume, because R, you can find it from the table A to A as discussed. T1 is known, right? Make sure you know whether to use this in Kelvin or degree C, right? You should know that by now. And then PA1 is from here, substitute, you will get the value, and omega 1 is, again, substitute all the information that you've got here to find omega 1, and there are sufficient informations here for you to find H1 as well, right? So that is done for state 1, and then you repeat the same thing with different values for state 2, right? Now, how to find your m dot a1? So you are given volumetric flow rate. So for point number 1, this is your volumetric flow rate. So 20 meter cube per minute, right? So this is obtained from here. You divide it, that will give you in either kilogram per minute or kilogram per second, depending on how you change the values. All right. So you can find for both point 1 and point 2, and then for conservation of mass, this plus this at point 1 and point 2 will give you m dot a3. So that is up to that. Well, then we continue. Remember, I showed you this formula. So once you know your m dot a1 and m dot a2, equate it to this to get your omega 3, and then you equate it to this enthalpy relationships to get your H3. So since H3 is known, right, so we can then substitute it into this formula, right, which is also equals to this. We can find Cp. Omega 3 is known, T3 is known, not known, right? T3 is what we want to find, and H3 is obtained from here. So equate this formula equals to H3, find out what is your T3. So that will give you the temperature at point number 3, right? So omega 3 again substitute into this, you will get omega, what do you call that, partial pressure of vapor at point number 3, and then that will be able, you will be able to use that to find your relative humidity at point 3, right? So once you've got that, and then you should be able to get what is your uh, volumetric flow rate, right? Once you've found out your specific volume at point 3 using this relationship, and that will be the end of solution for the example that we've discussed. So there are many applications, right, of air conditioning processes. So here we'll discuss very briefly on what you have. For an example, in our classes at Faculty of Mechanical Engineering, so you will see that you, in your class, you will always have one written air duct and one supply air duct. So what happens is the air goes into the written air duct, it is filtered, it's cleaned, and then it goes through the cooling coil, right, where heat is rejected. So as a result of that, the air is cooled, and then this is supplied with the help of a fan, right, into the supply air duct, and then this is channeled back into the room, right? So this system here can either be a heating coil or cooling coil. For Malaysia, we are using cooling coil, but if you are in UK during the winter climate season, then you will be using heating coil here to heat up the air, right? So this is fan coil unit that you have. Now if you have air conditioning system in a hospital, so in hospital, priority is to maintain a bacteria free air supply. So there you need to ensure that your air conditioning is supplying clean air. All right, so it has to be independent, all right, for different departments. So your rooms, wards, and all those things might have different supply of air. All right, so again you need to prevent some sort of a cross contamination for the return air, right? So they usually do not use it, right? So that is why they mix it with fresh air. And you also have this HEPA filters. So what is HEPA filter? Because you want to filter the air so that you can remove the bacteria, viruses, and so on. So they use high efficiency particulate air HEPA filter. Right. So this is some sort of just a brief introduction to you on how they use air conditioning in a hospital. So we also have air conditioning in printing shop, right? So in printing shop, you use multiple of colors for each pass of printing. So the paper is passed from one press to another. So ink from the first press must get dried before it reaches the second press, right? So to dry that, you need some sort of air conditioning, right? So because if the ink is not dried and then you superimpose another ink, so the color will get damaged. So the other thing that you need to take into consideration in a printing shop is the paper should not shrink, right? So if the paper starts shrinking because of overheating and cooling, your picture will have some sort of distortion, right? So you need to then control the temperature and humidity. So improper temperature and humidity may result in poor printing quality, right? So these are some of the things that you need to consider for printing shop as well. The last one that we're going to cover now is cooling tower, a section on cooling tower. So cooling tower is nothing but a heat rejection device. So it extracts waste heat to the atmosphere through the cooling of water stream to a lower temperature, right? So we have power plants, large air conditioning system, and some industries they generate large quantities of waste heat, and this waste heat need to be rejected, right? And what we do is we use cooling water from nearby lakes or river. So that was how traditionally it is done. So in some cases the cooling water supply is limited or thermal pollution is a serious concern. So in such cases the waste heat must be rejected to the atmosphere. So with cooling water recirculating and serving as a transport medium for heat transfer between the source and the sink, which is the atmosphere. So one way to achieve that is by using some sort of a cooling tower, right? So it is more like an evaporative cooler, right? So there are many applications for cooling towers, right? So you can use it to provide cooled water for air conditioning. You can use it in manufacturing plant. You can use it in electric power generation, right? So the idea of cooling tower came from spraying pond, right? So you can find out more information on online what is a spray pond, but the idea of cooling tower actually came from here. It's more on evaporative cooling, right? This is a typical cooling tower that you have, right? So let's say this is the heat generation process. So what we need is we need to absorb the heat out of this process. So the heat is absorbed by the water which is being circulated. So this hot water is then sprayed, all right, into tiny particles here. And then if you notice we have a fan motor. So this fan motor is rotating, which is absorbing cold air from the atmosphere. So you have two conditions now. The droplets of hot water are going downwards and they are interacting with the cold air which is coming in the opposite direction. Now as a result of that, there will be heat transfer between the hot water droplets and the cold air that is interacting. So as a result of that, the heat from the hot water droplets will be transferred to the cold air. And this cold air, after the heat transfer process takes place, will become hot air, and the hot air will then be rejected from the cooling tower. So as a result of that, this water is cooled, and then it will be resupplied back into the heat generation system to reabsorb the heat, and the process is repeated again and again. Right now, since the cold air coming in interacting with the water droplets here, it will get saturated. In other words, it will take away some of the water vapor together with it when it becomes hot. As a result of that, you will lose some moisture. So you will always need to supply some makeup water so that your water level is always maintained in a cooling tower. So these are the types of cooling tower that you have. You can categorize them either in mechanical draft cooling towers. So these are mechanical draft where the circulation of air is induced by the fans running with the help of an electric motor. You also have natural draft cooling towers. So these are mainly used in nuclear power plants, as you can see here. So they don't have any fan, so they rely on the buoyancy effect of hot and cool air rising. So the water is pumped into the natural draft cooling tower. and then the droplets, as it falls down, it heats up the air. So the hot air will rise, all right, taking away the heat from the hot water droplets, and the cold air will go into the natural draft cooling tower through these openings here, right? So the difference between natural draft cooling tower and mechanical draft cooling tower is that the mechanical draft cooling tower is very compact, but it uses a lot of energy. Natural draft cooling tower requires very tall structures, can be as high as 40 to 50 meters in height, and but it's not using any energy to induce the draft in the cooling of the water droplets that are coming out from the heat generation process here. So those are the types of cooling. We can also classify cooling towers according to different categories here. You can have counterflow induced draft cooling tower, cross flow induced draft cooling tower, and also have counterflow forced draft. These are some of the diagrams. So this diagram shows the counterflow induced draft cooling tower, and here you have cross flow induced draft cooling tower. Now, cooling tower maintenance is a very important issue. So there are a few aspects that you need to pay attention to. So one is you need to have inspection of the tower fan, condenser water pump, fill water basin, and the drift carryover to ensure satisfactory operation of your cooling tower. So that is why you need to have scheduled maintenance for cooling towers. You must also have periodic blowdown, right? So you must always clean the wetted surface and effective water treatments to prevent any formation of scale and dirt, as well as the growth of microorganisms on these wetted surfaces. All right, so this is required periodically, and not forgetting, because most of our mechanical draft cooling towers relies on a lot of moving parts, so you must have this periodic lubrication of most of your moving parts for the tower as well. So this is what we have in our faculty of mechanical engineering. So if you go to level 10 or level 11 on the rooftop, you can see a series of cooling tower, right? So you have hot water being supplied from the chiller, right? So they come in at certain temperature, and then after going through the cooling process in a cooling tower, you will see that the temperature drops, right? So there's a significant temperature drop in the what do you call that, uh, chilled water that you use for the cooling processes in our air conditioning system. This is again, so condenser water supply return, all right, from the cooling tower. So this is CWR, means chill water return, CWS means chill water supply, right? So this goes into our air conditioning process. After that, the heat is absorbed and then it goes out as chill water return, and then this will be cooled by our cooling. So this is what we've discussed just now, makeup water, right? So makeup water is introduced into the cooling tower so that you maintain uniform level of water at all times in a cooling tower, right? So you can do that by using a float valve, right? And then since this water is stagnant, you need to have some sort of a water treatment so that you don't have any algae forming here, right? And also you need to be aware of so that this pool of water in a cooling tower will not become a breeding ground for eddies. So some sort of a water treatment is required. Now let's look at our next problem. So this problem is related to our cooling tower. So here we have cooling tower water that leaves the condenser of a power plant and enters a wet cooling tower at 35 degrees C at a rate of 100 kilogram per second. Water is cooled to 22 degrees C by air that enters the tower at 1 atm. So now the question here is using 1 atm. So you can safely use the psychometric chart to solve problems related to this problem here. So 20 degrees C, 60% relative humidity, and leaves saturated at 30. So the question says it leaves saturated. Saturated means your relative humidity is 100% at this temperature. So neglect the power input to the fan. Determine A, the volume flow rate of air entering the cooling tower, and B, the mass flow rate of makeup water required. So for this, I've again prepared a skeleton for the solution. So let's discuss the skeleton together. So these are the things that you need to find. So this is the skeleton. So I hope you can fill in the blanks on your own, right? So let's discuss how to do this. So this is the schematic diagram that illustrates the problem. So you have warm water coming in at 35 degrees C at this rate 100 kilogram per second. So it's sprayed down. So air is used to cool down. So it is coming in at 1 atm 20 degrees C, relative humidity given at 60%. So this then interacts and then leaves at hot air at relative humidity 100% because in the equation is mentioned is saturated. So the cool water will then accumulate at the bottom of the cooling tower and then it will be resupplied into the process, all right, with the same flow rate. Now from 35 degrees C, because of the cooling tower, it has dropped, the temperature has dropped to 22 degrees C. So we need to find all these value. So enthalpy of saturated liquid water is, so you find this value at 22 degrees C. So again at 22 degrees C, you find what is the enthalpy. All right, so you need to do some sort of interpolation here. All right, and 35 degrees C is given here, so straight away you can find what is the enthalpy, and then from the psychometric chart you can find what is your H1, omega 1 and specific volume for point number 1 here. All right, point number 1, and for point number 2, which is here, you can find H2 and omega 2. So once you have that, so these are your dry air balance equation, water mass balance equation. So you find the difference between m dot 3 minus m dot 4, that will give you the amount of makeup water that you need to introduce. Because remember, relative humidity 60% at 0.1 goes out saturated, that means you are taking away some moisture, and how much of that need to be replaced is given by the makeup water, and that can be calculated using this formula. So based on energy balance, right, and then you simplify it, and this is the m dot a that you need to find. So m dot 3 is given, right, so 100 kg per second. H3 H4 can be found, right, and H2 H1 is known, omega 2 omega 1 is known, H4 is known, right. So this is your H1 at 22 degrees C. If you look at 22 degrees C, H4, and then 35 degrees C is your H3. All right, H1 and H2 is from here. Substitute, get your m dot a. Volume flow rate can be found using this formula, and then your makeup water is given by this formula. All right, so try this question, try it on your own, see that you are able to do. With that, that will be the end of our air conditioning. So hopefully after this chapter you know how to do some simple processes in air conditioning. You know how to use the psychometric chart to solve problems related to air conditioning, and you also know how to do problems that are not solvable using psychometric chart, whereby the pressure is given uh, beside the atmospheric pressure, all right, 1 atm, and then you got to use all the equation to solve the problem. So with that, we'll end this chapter. Thank you.